In 1975, a fishing vessel off the coast of Massachusetts hauled up something the crew wasn't prepared for. A great white shark, over 7 meters long, heavier than a pickup truck. When marine biologists later examined the jaw, the teeth stopped them. Not just large, but architecturally strange. Serrated not along the edge but in layers, each microserration angled differently, engineered to cut through bone, muscle, and cartilage with almost no drag resistance at all. The biologists said the same thing, almost word for word. It looks over-engineered, like whatever built it had too much time. Here's the thing. Whatever built it had 450 million years. Across 5 mass extinctions, across ice ages and asteroid impacts and oceans that turned to acid, the blueprint of what a shark is has barely changed. Not because evolution forgot about sharks. Because every time it tried something different, the original kept winning. That is not how evolution is supposed to work. Evolution is relentless revision. Constant pressure, constant failure, constant replacement. The vertebrate body plan has been rewritten so many times the original is unrecognizable. Fish became amphibians. Amphibians became reptiles. Reptiles became mammals and birds and everything in between. The history of life on Earth is a history of radical reinvention, whole body plans scrapped and rebuilt under the pressure of a changing world. Sharks watched all of it happen and didn't move. The deeper you go into their biology, the more that stops being a curiosity and starts being genuinely difficult to explain. Start with the skeleton. Sharks have no bones, not a single one. Their entire internal structure is cartilage, the same flexible material in your nose. To most people that sounds like a flaw. Bone is hard. Bone is what we associate with strength, with structure, with the ability to withstand force. Cartilage sounds like something evolution hadn't finished yet. But look at what cartilage actually does inside a shark's body, and that assumption falls apart. Cartilage is roughly half the density of bone, which means a shark's skeleton weighs almost nothing relative to its size, giving it a natural buoyancy that bony fish compensate for with a swim bladder, a gas-filled organ that has to be constantly adjusted as depth changes. Sharks don't need one. And cartilage doesn't just flex under pressure. It compresses and rebounds. In deep water, where pressure is enormous, a rigid skeleton fractures. A cartilaginous one absorbs. Evolution didn't give sharks cartilage because it ran out of better ideas. Cartilage in water, at depth, under force, outperforms bone in almost every meaningful way. But that decision comes with a cost. Cartilage dissolves. It doesn't fossilize, which means the physical record of shark history is almost entirely missing. What survives in rock, what paleontologists pull from ancient sediment, are teeth. And shark teeth are extraordinary things. They don't sit in fixed sockets the way ours do. They grow in rows, stacked behind each other in a continuous conveyor system, new teeth forming at the back and migrating forward as the front row wears down or breaks. A single shark might cycle through 50,000 teeth in its lifetime. Some species replace a full row every 2 weeks. The tooth is disposable, which means it never needs to be permanent, which means it can be optimized purely for function rather than longevity. The earliest confirmed shark teeth date to roughly 450 million years ago. But here is what makes those specimens strange. They are too refined for a beginning. The microstructure, the geometry of the serration, the way the enameloid is laid down. It all suggests a lineage that had already been iterating for a long time before that point. The very first shark fossils we can identify don't look like prototypes. They look like a design already deep into its 2nd or 3rd generation of refinement, which means the actual origin of sharks may be older than anything we've found. We may be looking at the middle of the story and mistaking it for the start. What that early story eventually produced was Helicoprion, a shark relative from around 290 million years ago that solved the problem of teeth in a way nothing before or since has attempted. Instead of rows of replaceable teeth, Helicoprion grew a single continuous spiral of them, a whorl coiling inward on itself like a circular saw embedded in living tissue. For over a century after the first fossil was found in 1899, paleontologists couldn't agree on where in the animal's body that spiral sat. Early reconstructions placed it along the snout or curling grotesquely from the lower jaw, like an appendage. It wasn't until CT scanning of a specimen preserved in phosphate nodules that the answer emerged. The spiral sat entirely within the lower jaw, tucked inside the mouth, rotating as the jaw closed. Soft tissue impressions in the rock showed the upper jaw had no teeth at all. Helicoprion's prey, likely soft-bodied cephalopods, was drawn in and hit by a rotating blade of interlocking teeth that sliced and pulled simultaneously. One of the strangest feeding mechanisms in the history of vertebrate life. And it persisted for roughly 30 million years. But Helicoprion was a branch, not a trunk. The lineage that leads to every shark alive today went a different direction. Leaner, more sensory, built around a system of perception that has no close equivalent anywhere in the animal kingdom. Sharks can detect a single drop of blood diluted across an Olympic swimming pool of seawater. Their nostrils aren't connected to breathing at all, dedicated entirely to chemoreception. Two separate channels of water flowing continuously over folded sensory tissue, each nostril sampling independently, letting the shark triangulate the direction of a scent by comparing signal strength on either side. That alone would make them remarkable hunters. But smell is almost incidental compared to what comes next. Clustered across a shark's snout, almost invisible against the skin, are thousands of small pores filled with electrically conductive gel. These are the Ampullae of Lorenzini, and what they detect has no analogy in human sensory experience. Every living animal with a functioning muscle produces an electric field. The contraction of a heartbeat, the firing of a nerve, the movement of a fin. All of it radiates outward as a faint bioelectric signal. The Ampullae of Lorenzini detect those fields directly. At close range, they register signals as weak as 5 billionths of a volt per centimeter. Sensitive enough to detect the bioelectric field of a flatfish buried completely under sand with no part of its body exposed to open water. A shark doesn't need to see its prey, doesn't need to smell it. If it is close enough and the heart is beating, the shark feels the electrical signature of that heartbeat through the water. This system appears in the earliest shark fossils we can analyze with enough detail to look for it. Evolution landed on electroreception hundreds of millions of years ago. In all the time since, it hasn't been replaced or significantly restructured, because nothing that came after it worked better. Alongside this runs the lateral line, a pressure sensing system embedded along both flanks of the body, detecting water displacement with enough sensitivity to feel the bow wave of a fish swimming several body lengths away. A shark operating in complete darkness, no scent trail, no visual target, builds a three-dimensional map of everything moving around it through pressure and electricity alone. It perceives the ocean in a way we have no framework for imagining. So why, carrying all of this, have sharks changed so little? This is the question that sits at the center of shark biology and doesn't have a fully satisfying answer. The phenomenon is called evolutionary stasis, and sharks are the most extreme example of it among vertebrates. The body plan, the sensory architecture, the cartilaginous skeleton, the tooth replacement system. It solidifies in the fossil record hundreds of millions of years ago, and the core of it simply doesn't shift. What makes this strange is that stasis isn't passivity. Shark species diversified enormously. There are over 500 species alive today, from the dwarf lantern shark, small enough to sit in an open hand, to the whale shark, the largest fish on Earth, filtering plankton through a mouth wide enough to swallow a person whole. The ecological range is extraordinary. But underneath that diversity, the fundamental design stays locked. The leading hypothesis is stabilizing selection. When an organism is so well matched to its environment that any variation from the existing blueprint reduces fitness rather than improving it, evolution stops producing novelty. The mutations still happen. The variation still appears. But it gets selected out generation after generation because the original is still better. Sharks aren't frozen in time because evolution abandoned them. They're frozen because every alternative kept losing. And then we arrived. Shark populations have declined by more than 70% since 1970. Some open ocean species by over 90%. The oceanic white tip, once described by Jacques Cousteau as likely the most numerous large wild animal on the planet, is now critically endangered. A design that survived the Permian extinction, survived the asteroid, survived 450 million years of a planet trying to destroy itself, has been pushed to the edge of collapse in 50 years. The irony cuts deep. The same traits that made sharks nearly indestructible across geological time make them acutely vulnerable to what we've done to the ocean. Sharks reproduce slowly. They reach sexual maturity late. They produce few offspring. When a population is stable, those traits are perfectly adequate. When a population is being removed faster than it can replace itself, they become a death sentence. Evolution didn't build a contingency for us. It built a contingency for everything else. And for 450 million years, everything else was enough.